Hello everyone, and welcome to Lab 1 for the Medical Imaging Modalities course, ENGG 4040. This is your lab coordinator speaking, Ahmed. And today I'm going to be running Lab 1 for you. So here, the setup I have here on the left side of the screen here, we have the DeskCat software that we use to gather the data from the DeskCat system right here. And on the right side of the laptop screen I have here is going to be the lab manual, and we'll go through it together. I'm basically going to be covering the methods section so that you guys understand how the data you've been sent was extracted. And somewhere on the screen I'll also have a live view of the DeskCat system so that you guys can also see what I'm doing in real time in order to make sense of the images that we see. Alright, so let's begin. So Lab 1, image quality. Now before we begin, please excuse any errors or any wait times. I want to be as real and natural as possible so that as I figure things out, hopefully you can also figure things out at the same time. So let's begin. So let's jump in. So the goals of lab or the first section of Lab 1, so spatial resolution and modulation transfer function, is to calculate the MTF, so the modulation transfer function, line pair phantom. A line pair phantom is this phantom that I'm carrying right here. These are phantoms. Now phantoms come in different shapes and forms. This here is a different type of phantom. It's called a step phantom. A phantom is basically a volume of space that has a specific pattern that we place inside the DeskCat system that we then use to simulate a CAT scanning environment. Now this isn't a CAT scanner in reality, it's a simulation. There is a camera at the end of that cylinder right there. There's a motor up top here. This wire powers connects the motor to the light system inside the cylinder. There's a USB that connects that allows us to control the motor speed from the DeskCat software. There's also another USB connection at the end of that cylinder that also allows us to modify the camera settings, and you'll see that along the way as I go through the lab. So that's the first goal. So to calculate the MTF of the DeskCat system by scanning a line pair phantom, which is this guy right here, and then plotting and comparing the different settings from the data that you receive. So let's begin. Method. Start the DeskCat software, which I have here on the left. Create a new project. Do not load the phantom yet. All right. So I'm just going to go here and create a new project. I'll call this project ENGG 4040 Lab 1. Alright, so as soon as I create a new project, it automatically connects the camera of the DeskCat system. Adjust camera settings by going to Scanner, Camera Settings, Frame Rate, Shutter Speed. So let's do that. So Scanner, Camera Settings, Frame Rate, Shutter Speed, until a few red pixels appear in the camera video window. So let's see, I'm gonna adjust the frame rate right here. It says until a few red pixels appear. I'm just gonna go with a little bit more. There we go. What do you guys think? I think that's about right. A few red pixels. I'm gonna close that. Did I actually adjust it? 1 second. Yes, I did. Excellent. Step number 3. Select reconstruction, options, the Hamming filter. So reconstruction options, Hamming filter. Okay. So right, that's selected. That's awesome. So that's already chosen for us. Close it. And now step 4, calibration, geometry calibration, auto calibrate. So calibration, geometry calibration, auto calibrate. So it automatically calibrates the system for us. This is our source to axis distance, axis to detector distance, horizontal light size, vertical light size, axis of rotation. Now, calibration is very important for any system that you use in any course, in any type of lab environment. Basically, it sets the reference or the benchmark of normal of the normal environment. So I'm going to go ahead and do you accept these values? Hit yes. Auto calibration successful. Excellent. Gonna exit from there. Phantom setup. Acquire a reference image. So acquire a reference image. Select new reference image. Do not load the Phantom yet. Okay. So so new reference image, right there. Perfect. Reference image taken. Load the line pair Phantom into the scanner. Okay. Now I want you to pay attention as I actually do that. So there. This is my line pair Phantom. I'm gonna go ahead and open the rotor. You can see here that there are these teeth that basically encapsulate the phantoms very easily. I'm just going to go ahead and insert. Can I make sure that it looks clear and symmetrical? Looks great to me. I'm going to go ahead and put this back in. Now, as I do this, I want you to focus on the DeskCat software. You'll see as I place this phantom inside, there it is. There it appears. Our camera is working. Excellent. And you can see the lines very clearly. Excellent. Now, rotate the phantom. So step number 7. So after we, load the line pair phantom, that's excellent. Step number 7 asks us to rotate the phantom so it is exactly flat to the camera. I think we already have that right there, but let's just, for testing purposes, let's actually do that with the scanner. So, let's see, scanner, motor control. So if I go to scanner, motor control, here is our motor control. This allows us to rotate the motor that is, that basically is gripped onto the phantom. Hint, rotate the phantom so only the edge is visible. Then select set current position as home, and then move to 90 or 270. So rotate the phantom so only the edge is visible. Only, okay, so this, you guys see that? Alright, so this edge, I assume this edge is visible. I think it needs a little bit more. I'm not sure how we can do that. I think that's fine. Ah, there we go. So, this is the incremental feature where you can increment counterclockwise and clockwise. I think that's about right. What do you guys think? The edge is visible? That looks good to me. So, the edge visible, then select set current position as home. So I'm gonna select this position as home. Excellent. And then it says move to 90 or 270. I'm gonna hit 90. Boom. There it is. Looks really good. There's my 2 space 1.5 1 0.75 half and a quarter. Excellent. Gonna get out of there. Now let's start taking some pictures. So 2D acquisition. Open the projection viewer, select enable snapshot, and then take snapshot. So projection viewer. Select enable snapshot. There we go. And then take snapshot. Done. Right. And then it says select the line profile tool. I'm not sure. I hope it did take the snapshot. let's just go ahead and load that image. Scan data. Scan reference. Huh. Okay, so this is our snapshot. I guess it takes the cat image. Okay, that looks good. Step number 9. Select the line profile tool. There we go. Draw a line which intersects the line pairs. Figure 2. Right click on the line profile and export data as CSV file. So I'm gonna basically, if you see this red line right here, they want us to draw a line that's intersecting all these lines down here. So let's do that. Have my line profile tool. I'm gonna start drawing this, going down from the top. Ooh, look at that. You see this? This is interesting. Let's go back up here. So the 2.0, obviously, there's a greater distance between the lines. So that is why those pixels are a little bit wider. The 1.5 are a bit shorter. The 1 gets smaller. 3/4, half, and 1/4. That looks pretty neat. Okay, go ahead and set that there. Looks excellent. Now it says right click on the line profile, export data as CSV file. Right click. Whoops. Let's do that again. Let's go down here. Right. Oh, sorry. I had to right click the graph and not the line there. So right click, export data as CSV. I'm just going to go ahead and just put it in documents here. I'll just call this line profile ENGG 4040 lab 1. Done. Excellent. Let's keep going forward. I'm going to close that projection viewer since we're done this section. Let's move on. Let's move on to CT acquisition basic. Okay, so we're almost done here. Perform a data scan of 320 projections with a line pair phantom loaded, which we already have. So let's do that. So data scan, scanner, is it the scanner? Oh, no, my bad. So data scan is right here on the left pane under scan. So start data scan of 320 projections. So as you can see here, there are these small rotations that are happening, and every rotation that takes place, there's a projection being taken and being laid out into the slice sinogram here at the bottom. So these are 320 projections, i.e. 320 slices. Almost there. Excellent. Select side panel, voxel size very high. So where is that? Voxel size very high. Perform a reconstruction. Excellent. That's complete. Step number 12. Maximize the 3D viewer. This guy right here. So each of these 4 views are different, basically different views of the system. So the top left quadrant here is a camera video. The bottom left quadrant is a center slice sinogram. The bottom right quadrant is a 3D viewer. We have 4 categories: MPR, which stands for multiplanar reformatting, isosurface, MIP, and density sum. And the top right quadrant is a slice reconstruction. So I'm going to go ahead and maximize the 3D viewer right here. And now it says rotate the cube, or actually select multiplanar reformatting, which we have right there, this guy right here. Rotate the cube so the center line, that's type right there. Oh, sorry, the entire line pair pattern is visible as close to flat as possible. So let's try to rotate this cube. It's interesting. So I need to adjust the level. There we go. As close to flat as possible. That looks about right. Okay. Use the line profile tool again. Figure 3, and export data as CSV file. So I'm going to go ahead, create a line down here, or actually I think it's this one right here actually. Okay. Line profile tool. I'm going to draw a line down there again. Excellent. And I'm going to export data as CSV file. So this will be the CT acquisition. CT acquisition ENGG 4040 lab 1. Excellent. So we're done the CT acquisition section. Now CT acquisition variations. Repeat steps 11 and 13 with side panel, voxel size high, and then repeat steps 11 and 13 after selecting reconstruction. Reconstruction options, no filter. So let's do that really quickly. So voxel size high this time. Reconstruction. That's complete. As you can see, it's a little bit blurrier the voxel size has been reduced to 0.5, and as you can see, it's not as clean as before. So let's do that again. Create a new line. Export that. 11 to 13. So the CT acquisition, and I'll call this voxel size high. Now the same thing this time, but select reconstruction options, no filter. So I'm going to go to reconstruction right here, options, no filter. So we're doing voxel size very high again, but this time with no filter. Just to double check, no filter. Let's go ahead and reconstruct. A reconstruction at this resolution already exists. Do you wish to overwrite? Yes. Because this time we're doing it with no filter. Okay, reconstruction complete, and wow, as you can see, without the filter, it does look much different. The light intensity seems to be harder to view the lines. So what I'm going to do is I'm going to find a level of light where I can at least see most of the lines, and go ahead and create a new line and export that. CT acquisition. Voxel size is going to be very high. And this time, no filter. Gonna hit save. And that is it for part 1 of Lab 1. Stay tuned for part 2 of Lab 1 very soon, which will include edge response, point spread function, and MTF. See you soon. Welcome back. We're now going to begin Lab 1, Part 2, which is the edge response, point spread function, and MTF. So please go ahead and review the lab manual here for the introduction section to go over some equations, as well as go over some of the graphs here to get a better understanding of what we're about to do next. The goal of this section of Lab 1 is to measure the MTF using the edge response technique. So that's going to be using our edge response phantom that you can see in the video right here. And then to determine if the desk system is shift invariant is the second goal. And the third goal is to compare MTF curves under different imaging conditions. So let's begin. Set up the desk CAT system. So the first section is system setup and calibration, which is very important. Guys, whenever you're setting up new equipment, it's obviously it's much better if you're here. Unfortunately, due to the current situation, you're not able to experience that. But just keep in mind that whenever you're setting up any equipment, any piece of hardware, whether it's in this course, in your work, in a chemistry lab, engineering lab, machining lab. Calibration and setup is very important, right? We want to make sure our machines and our equipment and our hardware are good to go and have, you know, the environment in mind before we go ahead and collect data. So set up the DeskCAD system again, adjust the shutter speed for a few red pixels. So let's go ahead and do that. So shutter speed. So we have the views here we have is from the first section. So don't worry about that. So let's just go ahead and adjust the shutter speed of our camera. So scanner, camera settings, adjust shutter speed until a few red pixels are available. That's too much. That's about right, right? That's too much. There we go. A few red pixels. Excellent. And adjust the Hamming. So select Hamming filter under reconstruction. Since we disabled it last time, so Hamming has been selected. Now, do feel free to search what the Hamming filter is. I'm sure you can find an explanation somewhere on Google or in your course lecture notes. So Hamming filter. And then hit auto calibrate for the motor. So if we go to so not the motor, just the geometry calibrations. So I'll hit auto calibrate. Shouldn't have changed too much. Or actually, maybe it did. So I'm gonna accept that. That's fine. Done. In the calibration section, record the value of horizontal light size. Calibration section. Record the value of horizontal light size, which is 12.09. You will need this later, so let's keep that in mind. So I'm gonna write that down on a piece of paper. 12.09. Done. Phantom setup. Load the blank silicon phantom into the scanner. This guy right here, if you can see it. This is our blank silicon scanner. Just make sure that the camera is on. Yes, it is. So this is our blank silicon scanner that I'm going to be setting up into the system. Basically, to do that, I'm going to remove the rotor right here. Remove this line pair phantom from the first section of the lab. So to do that, I want to sort of take it out like that and insert the blank phantom. Make sure that's straight. So we want to make sure there aren't much rotations. Looks excellent. I'm going to put it back in, and as I do that, you'll notice that the blank, the camera video is now blank, which is how it should be. Excellent. So let's go ahead and take a new reference image. So acquire a reference image. This is the new reference image. So I'll take that new reference image. Reference image taken. That makes more sense. Estimating the ERF radiographic mode. So load the step edge phantom. So now that we've placed the blank phantom, we've taken a reference image for which we'll base off all our data from. I'm going to go ahead and replace that blank phantom with our step edge phantom. So I'm going to go ahead and replace that. Make sure it looks good. There aren't much rotations. It's symmetrical. Excellent. Place it back in. There it is. Perform a data scan of 320 projections. Let's do that. 320 data scan. Let's go. You'll see very soon why it's called a step edge phantom. I'll show you that very briefly. Ignore this line profile on the 3D viewer quadrant. This line profile was taken from the previous section. We'll be creating a new line profile for this particular phantom. Done. Alright, so the next step now is to select the data radio button. Now, there's a step missing here. This button is actually found in the 3D viewer, so let's expand that. Now that we have our projections, I'm going to go ahead and expand our 3D viewer section. If we go to line profile, main, let's see here. Right, so projection viewer. Let's open that up. My apologies, it's in the projection viewer pane. We're going to select the data radio button. And then it says select the full image checkbox. Done. Scroll through the 320 projections and find the projection image showing the sharpest edge, i.e. the one perpendicular to the image. Let's see. How do we do that? How do we scroll? There we go. Not very convenient. Actually, never mind. So let's find. The one showing the sharpest edge. There we go. Exactly there. So I'm going to go ahead and line profile right there. Use the line profile tool to draw a line which perpendicularly intersects the edge. Here is why they call this the step edge response, because when I place a line right there, you can see there is a step right over there. Sorry, here's the reason why it's called the step edge phantom, because as you can see here, the line profile of the pixels shows a step due to the large contrast of darkness of the dark areas and the bright areas. So now that I have my line profile right there, I'm going to go ahead and export data as CSV. I'm going to call this ERF 2D profile. Lab 1, Part 2. Done. Now, estimating ERFX CT is our next part of the lab. So select side panel, voxel size very high, perform a reconstruction similar to before. So now that we have that, let's start reconstruction. Let's close that. So there it is starting a reconstruction. Let's wait till that finishes. Right, that's complete. Maximize the slice reconstruction window. Scroll through the axial slices to the center. So 320 center would be right there. Okay. Use the line profile tool to draw a line on the center slice perpendicular to the step edge, a few millimeters from the axis of rotation. Ah, my apologies, I did not have this enabled. So the line profile needs to be enabled. There's a step missing there. Sorry about that. Let's go back here. Let's draw a line right over there. Actually, let's do it on the opposite. Let's start from here to there. There we go. So now we're gonna go ahead, export data as CSV. Call this ERF CT high res center. That's done. Repeat steps. Repeat step 11 at plus minus 40 slices from the center slice, plus 10 minus millimeters. You must redraw the line each time.